Hello again, physics friends. I'm going to work through a specific example from the textbook in which we can practice writing and using the Lagrangian and also thinking about stability and positions of equilibrium in that system. Okay, so the problem is as follows. We have a wire that's shaped into a parabola, and we're given the equation of that parabola. That wire is being spun about the z-axis. So the wire itself will sweep out a surface that's like a parabola of revolution. And on that wire, we have a bead of mass m that can slide freely without friction on that wire. Okay, and we are asked to write down the Lagrangian in terms of rho as the generalized coordinate. So this problem as framed is telling us there's only one degree of freedom, and that it's asking us to use as our generalized coordinate. It's saying please use for your generalized coordinate the cylindrical coordinate rho. I want to start by first making sure we're clear on why there's only one generalized coordinate necessary. Why is there only one degree of freedom? Okay, so we have one particle, which in general means that we would have three-dimensional motion, but we must therefore have two constraints, such that we end up with one degree of freedom. What are those two constraints? Well, number one, we're told that the particle moves on a parabola, so z and rho are not independent of each other. They're related through that equation of the parabola. So that gets rid of one degree of freedom. The other piece of information is if you think about cylindrical polar coordinates, there's three coordinates, rho, phi, and z. So now we see that z is not independent of rho, but also we are not free to choose our angle phi. Phi is fixed such that phi dot is this constant omega, which tells us that phi is growing linearly in time, starting from some reference position, and we can take phi naught to be 0 without loss of generality. We just kind of rotate the picture to where we want it to be to begin and then rotate it there. So the key idea here is that this angle phi in cylindrical polar coordinates is not a free parameter. The particle is forced to move such that phi dot is this constant omega, which is a given in the problem. So we started with, in general 3D motion, for one particle, we've applied two constraints. We end up with one degree of freedom, and we are asked to use rho, the cylindrical coordinate rho, for that generalized coordinate. Okay, so the general approach I'm going to take here is the kind of foolproof approach. Write kinetic and potential energy in Cartesian coordinates, x, y, and z, and separately write those Cartesian coordinates in terms of the quantities of interest, in this case rho, and in general you can also involve t for time. When you make that substitution, you therefore will have kinetic and potential energy in terms of the generalized coordinate rho and time. Okay, so let's see how this is going to play out. Okay, so if we first want to write t and u in terms of x, y, and z, we want to be able to express the position in terms of x, y, and z in terms of rho and t. So let's just refresh ourselves how to write Cartesian coordinates in terms of cylindrical polar coordinates. So I've annotated this diagram by drawing in the Cartesian axes. Z is already there. And I've kind of drawn it in a perspective where hopefully you can see the parabola here has a component kind of lies above the xy plane, but the projection of the parabola down into that plane is given by this dotted line. And so there's an angle phi associated with the position of the bead as drawn. It's right there. And so given that, we now see that, we'll call this steps A, B, and C. Step A is just to say that t is m over 2 x dot squared plus y dot squared plus z dot squared. And u is mg times the height, and the height is simply z. Okay, so now we're on to step B, writing x, y, and z in terms of rho and t. That's where these parameters are going to come in. So step B, we say x is rho cosine phi, y is rho sine of phi, and z is given by the equation of the parabola, which is k rho squared. Okay, so now our goal is to get rid of x, y, z, x dot, y dot, z dot in kinetic and potential energy and replace it with these terms. So what that means is we're going to have to find time derivatives of x, y, and z, square them, and combine them. So let's find the time derivative. X dot is going to involve a product rule. X dot is going to involve a rho dot and then a derivative of the cosine. So we're going to have a rho dot times cosine phi minus rho phi dot sine of phi. Right, so derivative of cosine phi is sine phi, chain rule that, derivative of phi with respect to time is phi dot. Same thing's going to basically look, things are going to look pretty much the same for the y coordinate. We're going to have a rho dot sine, this time plus rho phi dot cosine. And we have that z dot is given by 2k rho times rho dot. Okay, so in order to find the kinetic energy in terms of our generalized coordinate of interest, we need to find v squared, right? Which is the x dot squared plus y dot squared plus z dot squared, okay? I'll write it down here. So x dot squared, I'm going to get three terms. Rho dot squared cos squared plus the square of the second term plus 2 times the cross term. Like so. That's the x dot squared. We add to that y dot squared. And we get the same cross term, except with a plus sign instead of a minus sign. So that's good. We're going to get a nice cancellation there. And I'm just going to highlight these. So my x dot squared is this first row. My y dot squared is the second row. And then my z dot squared will be 4k squared rho dot squared. Okay, these first terms, I get a cosine squared plus sine squared with the same prefactor. So I just get the prefactor. The same thing is going to be true with these two terms. I get a sine squared plus a cosine squared with the same prefactor. So I just get the prefactor. And then these two final terms are going to cancel because they're equal and opposite. And then I have my z dot squared term, which is 4k squared rho dot squared. So now I have a kinetic and a potential energy, which means I have a Lagrangian. And my Lagrangian will involve rho dot, and time. Okay, and why do I see that it's going to involve time? Well, remember, phi dot is not an unknown function. Phi dot is omega, the rate that the parabola is spinning. And we are told that that rate is constant. So I'm going to come back to this equation, and I'm going to write it only in terms of rho and the constant omega as well as rho dot. There is some. So we have here rho dot squared plus omega squared rho squared plus 4k squared rho dot squared. That's our v squared. And so when all is said and done, we finally end up with an expression for the Lagrangian. As shown here, it's m over 2v squared minus mg times the height z. So I've moved things around just to buy us some space here. We have our Lagrangian, and now we're trying to find the equation of motion for the bead and study the motion of the system. So there's one Lagrangian here, but there's also only one Euler-Lagrange equation because there's only one generalized coordinate. That coordinate is rho. Okay, so we're going to need to compute partials of the Lagrangian with respect to rho and rho dot. Let's start with rho. We march through, there's 1, 2, 3, 4 terms. Rho doesn't appear in the first one, so that goes away. This term gives us 2 omega squared rho m over 2. So that's just omega squared rho times m. Like so. Second term, we're going to get an 8k squared rho dot times m over 2. So that's 4 mk squared rho dot squared. And the final term will get minus 2 mgk rho. We similarly look at the partial with respect to rho dot, and we get the following: m rho dot plus 4 mk squared rho dot, and that's it. The final piece is that we have to take the time derivative of that second partial, and we get m rho double dot, but then we have a product rule on the second term, plus 8 mk squared rho times rho dot, and we get 2 factors of rho dot, one from before and one from the time derivative. And then we also have the derivative of the second term, which is the rho dot term. So rho dot becomes the rho double dot. Now our Euler-Lagrange equation tells us how to combine those two partials. And it says d dt of the partial with respect to rho dot is equal to the partial of L with respect to rho. Okay, so we see a couple things. First of all, every single term has an m in it, so we're just going to drop the m because it cancels on the left and the right side. And then we can also do some grouping. So we have 2 terms that are rho double dot, so we're going to group those 2 terms on the left-hand side. Rho double dot, 1 plus 4k squared rho squared. Then we have this piece that's not yet grouped, 8k squared rho dot squared. That's the time derivative piece. And then now we have the generalized force piece, which is up here. But again, we can group some terms. In particular, we're going to group this first term and the last term, which has a factor of rho. And we're going to leave the middle term alone for now, but we'll see that it will combine with the term on the left. So we have minus 2gk minus omega squared all times rho. Now notice that we have a term on the left and term on the right of the same structure. One is twice the other, so we can merge those together. And at the end of the day, we have second derivative of rho is added to 4k squared rho dot squared, because we've gotten rid of one factor on the left, and that all equals minus 2gk minus omega squared times rho. And so this is our Euler-Lagrange equation for rho. It's the second order differential equation. It is quite messy, right? We have nonlinear terms. We have cross terms between position and velocity. So this is going to be tricky to solve in general. But we're not asked to solve it in general. We are asked, however, to see if there are positions of equilibrium, that is, values of rho that are constant. So as the wire spins, the bead stays a fixed distance from the z-axis. Remember, rho is the distance, the perpendicular distance from the z-axis out to the point of interest. Okay, well, if we're asked about that, we're basically values of rho at which the bead can remain fixed. What that means is that rho dot and rho double dot are both 0 because rho is a constant. So we can now simplify. So if we look for rho equals constant solutions, meaning that rho dot and rho double dot are 0, that means we can simplify our expression. So the first thing is this whole first term is gone because it's rho double dot. This whole second term is gone because it involves a rho dot. So all we're left with is this, and that tells us that 0 equals minus 2gk minus omega squared rho, and that implies that we need omega to equal the square root of 2 times g times k. That gives solutions with constant rho. There is, of course, one other way, and that is if rho itself is 0, then that satisfies this equation too. So there's another case, which is rho is 0. What that means is that your bead is sitting down at the origin, and as the parabola spins, the bead will remain at the origin. Okay, so both of these are solutions. So we have solutions, but now we want to understand, are these stable or unstable equilibria? So let's work on that. Okay, so now we've found these equilibrium positions, bead right at the vertex of the parabola, or bead anywhere on the parabola, but the rotation is given by this specific amount, which depends on the curvature of the parabola. The question is, are these equilibrium positions stable or not? So let's go through. Let's start first with the bead at the origin and see if that's stable, and then we'll look at the other case. We can come back to the original Euler-Lagrange equation and put in rho equals 0, right? So we're going to lose this term, we're going to lose this term, we're going to lose this term, and we're going to find rho double dot is 0. But of course, we're interested in small nudges away from that equilibrium. So we want to say, we want to let rho be 0 plus a deviation from 0, a small deviation, where epsilon is this small deviation. And we can then compute derivatives like that. And we can put those into our equation of motion, our Euler-Lagrange equation, and we can ignore nonlinear terms. Okay, so put rho equals epsilon and so on back into the Euler-Lagrange equation and linearize. This means keep only epsilon dot and epsilon double dot to the first power, drop epsilon squareds, epsilon dot squareds, epsilon double dot squareds, and higher order terms like epsilon cubed and so on. Okay, so here we can just do it. I mean, it's basically the same equation of motion. We just are replacing rho with epsilon. Okay, so we have epsilon double dot, 1 plus 4k squared epsilon squared. That term's going to go to 0, plus 4k squared epsilon dot squared. That term's going to go to 0. And then minus 2gk minus omega squared epsilon. Okay, so terms that are going to go to 0. We're going to ignore the epsilon squareds, whether dotted or not. And so now on our left-hand side, we just have an epsilon double dot. That's it, times 1. And on the right-hand side, we have minus 2gk minus omega squared epsilon squared. This is an equation of motion that looks a lot like a mass on a spring, right? I mean, it's a function's second derivative gives you back minus a constant times that function. So this is stable as long as the term in the parentheses is positive. So this is stable if 2gk minus omega squared is positive, so that the overall relationship between epsilon double dot and epsilon has an overall minus sign. Okay, so we have a condition now. As long as we're not rotating too fast, then we're going to be stable at the origin. How fast is too fast? Well, if you're rotating so fast, if omega squared is larger than a multiple of k, which is the curvature of that parabola. All right, so that's how it plays out for case 1. What about case 2? So the condition here is omega squared equals 2gk, and it does not depend at all on rho. So we can't really do an expansion in rho because we could be anywhere on this parabola and move even large amounts and still be in a stable, still be in an equilibrium. But we want to find out if it's a stable equilibrium or not. So what do? Well, we take the condition for equilibrium and we put it back into the Euler-Lagrange equation. And when we do that, we're going to find this right-hand side goes to 0. So that's what I've done here. I've taken omega squared equals 2gk, put it in here, get 0. I've moved this term to the right-hand side, picked up a minus sign, and so I have this expression now. So this is the relevant Euler-Lagrange equation under the condition of a very specific angular speed for the parabola. So how do we deal with this? Well, we have to pay attention to some of these terms. Everything in this parentheses is a positive quantity, right? Rho squared, k squared, 4 and 1, they're all positive. So this whole thing is greater than 0. The 4, the k squared, and rho, those are all positive quantities also. How do I know rho is always positive? Well, rho is defined, you can't have a negative rho. It's a distance from the z-axis. So rho goes from 0 out to large positive values. So how do I compare these two equations then, the two sides of this equation? On the left I have rho double dot times a positive quantity. And on the right I also have everything positive, right? Even this rho dot squared, that's also positive. Okay. And yet I have this overall minus sign. So the collective right-hand side is negative. That must mean that rho double dot is negative. So my conclusion here is that rho double dot is negative. Otherwise, there would be no way for this equation to hold because the right-hand side is negative and everything in the parentheses is positive. So this tells us that rho double dot is negative always. Okay, so what does that mean? If you have on the parabola, you have the bead, and you give it a little nudge, let's say you nudge it up the wire, that's an increasing rho. Rho double dot is negative, that's an acceleration that pulling you back towards the origin, but even as you move outwards, rho will never get to 0. It will always be negative. So your bead is going to continue moving up the wire, slower and slower, but continue moving up the wire. The bead will never return to its position that it started at. And things are even worse if you nudge the bead towards the origin, because if you nudge the bead towards the origin, now the velocity is negative and the acceleration is negative, so it's going to move towards the origin faster and faster. Okay. Either way, whether you nudge it to the right or nudge it to the left, the bead is never going to come back to where it once was. So in all cases, this is an unstable equilibrium. In other words, the bead never returns to its starting point. Okay. But just to recap the kind of overall argument here, we had a Lagrangian, we derived an Euler-Lagrange equation from that, and we asked the question, is there a condition for which rho double dot and rho dot are 0, meaning that the position is constant. We found that there were. It turns out if you're at the origin, no matter how fast the system is rotating, that's a stable point. Sorry, that's an equilibrium point. Depending on the angular speed, it could be a stable or unstable equilibrium. For a very specific value of the rotation speed, you can put the bead anywhere on the wire and it will stay still. It'll just stay there, no matter where you put it. But if you give it a little nudge, it will move away in one direction or the other, never to return. So this second case is an equilibrium, with an interesting fact that it's an equilibrium at any given point, but all of those points are unstable equilibria. Okay, so this has been a quite detailed calculation. I wanted to go start to finish making the Lagrangian, finding the equation of motion, talking about stable points and unstable points and equilibria. So hopefully this has been an illuminating example for you. We'll have more practice in the future, but for now, take care and be well.